Okay, an integral domain is a principal ideal domain if every ideal is a principal ideal. So that's just the definition of what we call a principal ideal domain. It's only when the ring is an integral domain and you have a principal ideal domain inside it. A principal ideal inside it. We call that a principal ideal domain. And the only reason I'm giving you this definition is you see this definition places. So you might see this again. It's got a flag on it because it's inside an integral domain. That's all. So a couple examples. If you have a field and you look at the polynomials over that field, that's a principal ideal domain. And in fact, that's where I see this, is in books on polynomials. I'll see something like this. This is another example that I haven't brought into the class yet, but you could actually, you could take a field and say it doesn't have its root, and then extend that field. But you could do the same thing to a ring. You could take a ring where you might not have inverses and things like that, but you could still extend by a root. So you can take z, for example. I can make a polynomial which is formulated where coefficients belong to z, but the root itself doesn't belong to z. So in that, I could just extend in the same way. And that proof that I gave you the other day still holds. You still get that when you extend, the simple extension is going to look like this. So a plus bi, where a and b belong to z, and I is the root of x squared plus 1. And this turns out to be a principal ideal domain. The proof's messy, actually. You can actually go through it very similarly to how I went through showing that when you extend by just one alpha in a field, you can do something similar. And one more thing, I thought, I was going to skip this, but I think the analysts in the class would like this. A Euclidean domain is when you have an integral domain D, and you have 0 as the additive identity. You can kind of define a size metric. So if you take delta going from the non-zero elements of D to the positive integers, and it satisfies the following, that when you multiply, that the delta increases in size. And if you have two elements, and you can express the B by, you can basically do the division algorithm. You express the B as a cubed plus r, then it turns out that the delta of r is smaller than delta of a. So these conditions mean that you have a structured space where you can do the division algorithm. You can do the division algorithm on the integers, but anywhere else where you can do the division algorithm, that this object is called a Euclidean domain. But realize when you do the division algorithm, you need some notion of what you mean by size, because in the division algorithm you have something about r has to be bigger, equals 0, and smaller than q, or smaller than a. Because you have that notion of ordering something, you need some way to compare the elements to each other. So if you have some kind of messy looking group or ring, you won't be able to just tell, there's no notion of size. That's something that comes from analysis more, topology, right? So this delta gives you the notion of size. And that delta is called a norm. It's different than the definition of the norm. So let's test a little bit of real analysis. Where's the difference in the definition of the norm? Where do the outputs of the norm live? Lives in R plus, right? Right. So this is forcing it to the non-zero integers. So it's a little bit different. It's not quite the same. However, it turns out, so these are just some potential exam questions, and they're not hard, I swear. Like, you can just punch in the things, and they're physics proof. Sorry. Don't tell Mark. So you can just run through it and show it very quickly that this satisfies the condition of the abstract algebra norm, the Euclidean norm. Not Euclidean norm, the abstract algebra version of the norm. So leave it at that. The degrees, if you define the degree of a polynomial, that turns out to satisfy, very easy to prove. And the reason I brought up that z of I is not just to give you a different example. It does actually turn out to be the magnitude squared that you know of in the complex numbers. And then I gave you some just show me kinds of things to punch out to show if the following things are ideals. Use the checkability theorem to go through and just check through that these are ideals. Again, I don't think any of these are tough. I try to pick out things that you just go through the machine and check that it satisfies all the conditions. Okay, any questions?
Not yet.
Yeah, I think I just have to put a little bit more on that one proof, and that'll clean that one up. And there's a lot of definition here on just the norms, but when you do these examples, it'll be clear. And I haven't actually seen this. This is the first time I've seen the abstract algebra version of the norm. I've seen stuff like that before. So they have abstract algebra versions of what we mean by Hilbert spaces. I've seen those things, but I thought since we do a lot of analysis in this department, that some people would think this is cool. Okay, I'm pedaling right through. If you we can just do some of these problems in class on Wednesday just to slow it down, because it's easy for me to go fast if I'm just going through a PowerPoint. I'm going to do that.